All right. Good morning, everyone, and welcome to the third and last day, but possibly not least day in this NeSy workshop. I'm quite happy that the room is still quite full. I was like a bit worried, like it's the third day and it's right after breakfast, but yeah, happy to see a good number of in the audience. Yeah, for the spotlight today, we have three very interesting talks. Each talk is up to 30 minutes. So what I will do is, when it's 5 minutes left, I will show a sign. I'm going to try to keep some minutes for questions, so don't run out of 25 minutes. But then when you pass the 20 minutes, I will show you a sign of 5 minutes left. Then I will show you another sign of 2 minutes left, and then when it's no time left, I will be getting very close to you, so that we leave some time for questions. Probably you saw me taking random pictures during the workshop, like presentations and poster sessions. So yeah, feel free to check them out. And if you have some photos that you would like to share, just feel free to send them to me. If you are in a photo and you don't want to appear there, let me know as well. I can also remove you. No, for now, I just basically uploaded everything. So yeah, thanks a lot. And now the floor will be for our first speaker, Vitor Horta, that is presenting semantic interoperability of convolutional neural networks for by taxonomy extraction. To be connected, or you have enough battery?
Okay, good morning, everyone. It's an honor to be here with you today. Thank you for being here for the first talk in the morning. So my name is Vitor. I'll be talking to you about semantic interpretability of CNNs by taxonomy extraction. But although the title sets the focus specifically on CNNs, I want to start the presentation by trying to connect my work with not only CNNs or any type of deep model, but also any type of knowledge-informed model, and why not Neural-Symbolic AI models, okay? So allow me to put this in a very simplified way. When I think about a Neural-Symbolic model here, I'm saying about a model that receives not only input data, but some type of a prior knowledge during the training phase. And because we are guiding this model with some additional knowledge during the learning phase, we expect that they are going to have not only a higher performance in terms of a higher accuracy, but that they are going to be more efficiently during the training phase, so maybe requiring less data during the training. But more importantly, that they are going to be able to give us more richer, deep representation of the data, more semantic representations that will allow us to have more interpretable and trustworthy models, right? The question here is, we know how to measure performance, but we still lack some methods to make a quantitative comparison of interpretability and trustworthiness, okay? We usually create benchmarks that tries to put this in some type of performance metrics, like we do in computer vision, for example, when you try to compare models based on accuracy, precision, recall. But we know that we cannot measure interpretability and trustworthiness in the same way. And when we want to go beyond performance metrics, we usually rely on methods for explainable AI, okay? So especially in computer vision, which is the focus of this work, we have methods like saliency maps, visual case-based approaches, concept vector activations, which can get us some level of interpretability and explainability and comparison between models, but they still cannot create an objective quantitative comparison in terms of the semantic quality that the model has captured from a given data set or a given problem, right? And the challenge here is that, one of the challenges actually is that there's no ground truth for that, okay? So if I train several models for the same data set and I extract the deep representations from this model and I try to analyze it, There's no ground truth that I can compare and say, oh, this model here is the winner because, let's say, the representation that it acquired is closer to this specific ground truth. So our idea in this work is to think about ground truth, taxonomies as ground truths, okay? So the question is, what if we use taxonomies that we have out there as ground truths for semantic interpretability of deep models and to help us to compare between different deep trained models. And the idea for using taxonomies is first, we have this mapping between some existing data sets and existing ground truths. For example, we can relate and map the output classes for ImageNet with the entities in WordNet. And our idea is like, imagine that if you could train a model for a specific task on ImageNet, like an image classification, and suppose that once this model is trained, then you have the sub-symbolic representation there. Suppose that you can extract the taxonomic axioms that this model may have learned by being trained on this data set. And so if we can reconstruct and try and reconstruct the taxonomy, and we could possibly evaluate the axioms that we got from the deep representation and see if they are true according to the ground truth, okay? To try to check how many axioms we got. And there are two more reasons for using taxonomies, for considering taxonomies for this purpose. The first is that if you look at the existing works from the semantic web community, we do have ways to extract taxonomies from knowledge graphs and compare them back with ground truth taxonomies. So here are two examples of works that use DBpedia for that. And based on the work that I provided in my PhD, we got the idea that deep models can also be represented as graph structures if we consider a methodology called coactivation graph, which is not a computational graph, but a graph that expresses the interrelationships between neurons in a deep model. And then we can use graph algorithms over this type of representation and hopefully do taxonomy extraction by taking these methods from semantic web. So just to give a very brief overview on what a coactivation graph is, because it's important to understand the rest of this work. So a coactivation graph is a graph representation that connects every pair of a neuron within a deep neural network. Okay, so it's a graph where the nodes represents the neurons in a CNN or any other DNN, and the weighted edges represent the statistical relationships between the activation values. So we connect convolutional filters and neurons from any type of the layer in a deep neural network, and we create this complex network between neurons in a trained model. And to give an idea on how we can produce this type of graphs, we suppose that this is the neural network that we want to represent as a graph structure. The first thing we do is that we inject some input data to the model, and each neuron is going to output an activation value, right? So if we collect these values for all the neurons, we are going to have a list of activation values for each neuron in the model. And by comparing this list, we can compute a statistical correlation with them and achieve a correlation matrix that can serve as an adjacency matrix here. And from this adjacency matrix, we can derive a graph structure that we call the coactivation graph. And we have previously shown that once you have this type of graph, you can apply some interesting methods to achieve global explanations and local explanations for the CNN that the graph is representing. And in this work now, we're saying, okay, so if we have this graph, maybe we can do more than link prediction, community detection, and so on. Maybe we can do a whole taxonomy extraction here that will give us a better global explanation, semantic explanation for the model. The question is, how can we extract a taxonomy for coactivation graphs representing deep models, which is the first part of this work that I'm presenting here today. And we created this pipeline that takes 5 steps to go from the trained CNN to an extracted taxonomy. So the idea is, first thing, you have a training data, and you suppose that you have a corresponding taxonomy for that training data, but you do not use any type of private information during the training phase, okay? You train the CNN following the standard pipeline for training for image classification, for example. And also have a trained CNN, you apply the pipeline that I just showed for a coactivation graph, and you extract the coactivation graph for the CNN. Now, in this coactivation graph, each output class in your trained CNN has a node representation, and the next step is to go from this node representation to a vector representation using any type of embedding methods that we can have, for example, node to vec of SRP or any other thing. And when we are in the vector space, now the output classes are in this vector space, and we can apply a hierarchical clustering to achieve a hierarchy of clusters containing classes from the CNN. Okay? This hierarchy of clusters is still not a taxonomy, because we still need to do a last step of assigning labels to each of these clusters to match the labels from the ground truth taxonomy that we are trying to reconstruct. So let me illustrate to you how we can assign labels to clusters from a hierarchical tree. So the idea here is that imagine this hypothetical results from a hierarchical clustering, and suppose that you have a community like C1 and C2, clusters like C1 and C2, sorry. And here we will assign labels based on the number of classes in the cluster C, the number of classes of a type T, and the number of classes of type T in cluster C using this F-score. So the idea is the following. In C1, for example, we have 3 different output classes that were clustered together, okay? But all these classes are, they are subclass of a class car, okay? And because in this hypothetical example, all the cars are in this cluster, and this cluster only contains cars, then we get the maximum F-score for the label car and cluster C1. And we can assign label car to C1. So in C2, we have 2 dogs and 2 cats, okay? So the F-score is 066 for dog, 066 for cat, but when we try the label animal for this cluster, we get the maximum again, because all the animals in the data set are in this cluster, and this cluster only contains animals, okay? So in this case, there's no way we assign animal to C1 or car to C2, so we assign car to C1 and animal to C2, and we do this until we get to the root level of our hierarchy, and we extract this taxonomy. And then the question is, okay, it works, okay? We can extract taxonomies like this, but how can we use these taxonomies that we extract in this way to actually assess and evaluate the semantic representation of deep models? And the idea we proposed then was to calculate what we are calling the semantic adequacy of a CNN, okay? So it's like the semantic adequacy is how close the taxonomy extracted from a CNN is if we compare its axioms to a ground truth taxonomy. For example, model theory ImageNet, we compare against WordNet. And the idea is that if you have a ground truth like WordNet and the taxonomy extracted, we calculate the precision by checking how many of the axioms are correct, according to the ground truth, and we calculate the recall by checking how many missing axioms we have that are present in the ground truth but that are not present in our extracted taxonomy. Okay. So we do the precision recall in the F-score, and we do this for both a direct and a transitive evaluation. So the direct evaluation it's important because it measures for, if I say that a German Shepherd is a Shepherd dog, this is correct according to the direct closure of our taxonomy. And if I say, for example, that a German Shepherd is a dog, then it's incorrect because you need to have this Shepherd dog in the middle, right? I know you understand all of this. But then for the transitive evaluation, we also calculate F-score, but for the transitive closure. So now if I say that the German Shepherd is a type of dog, this is correct according to the transitive evaluation. And we have different values, one for direct and one for transitive evaluation. So, okay, so we proposed this idea, we implemented this, and then we did some experiments on 2 data sets, CIFAR 100 and ImageNet. And the interesting thing that I think here is what the models that we chose to try to get if the semantic adequacy makes sense or not. So the first thing we did is we extracted and we used this pipeline for an untrained VGG16 model. So just random parameters, and we expect that these models are going to give us the worst semantic adequacy values because it's just random parameters. Then we have VGG16, ResNet 18, and ResNet 152. And we also implemented one model that was proposed in 2018, which is the hierarchy-aware ResNet architectures, okay? And the idea here is the following. So in this type of models, instead of just having a standard pipeline for image classification, we inject some additional layers, intermediate layers in the CNN. And the role of these intermediate layers is to predict parts of the hierarchy of the data set that we are constructing. So for ImageNet, we don't try to predict, for example, if this is a German Shepherd dog, but you predict, oh, this is an animal, and the next layer, this is a dog, and so on until we get to the final class. So we expect that these models are going to have better semantic adequacy because this model has received some type of knowledge during the training phase, okay? And then we started to check the results for this. Before checking the semantic adequacy, we asked the following questions. So we first go to the co-activation graph to an embedding space. Does this embedding space can capture any type of semantics? So we computed the correlation between the similarity of these classes in this embedding space and their semantic similarity according to WordNet based on the distance between the two concepts in the WordNet hierarchy. And the two interesting things here are first that we found positive correlations, which gives us some indication that, okay, the embedding space that we are has captured some of the semantic similarities between the output classes. But the most interesting thing is that we have much higher values for the hierarchy-aware ResNets, which is the first evidence that the knowledge that we injected during the training phase allowed this model to capture better semantic similarity between the output classes. So when we calculated the semantic adequacy, these are the results for F-score. We got like somehow what we expected. So the first thing to notice here is that the untrained VGG16 achieves the worst results. And this was expected because here the model is not trained, okay? So we do not expect it to capture any good information about the data set. Then VGG16, when trained, gets better, and ResNet 152 gets better, but the best results were acquired again by the hierarchy version of the ResNet, which is again another evidence that the knowledge that we injected, even this not very smart way to inject knowledge during the training phase, we could have put more sophisticated methods, but even like this, we could help the model to get better taxonomic axioms. And we have this evidence that the knowledge that we injected has led to better taxonomies and more semantic representations. The results for CFAR 100 are compatible, so almost the same results. Worst results acquired by the untrained VGG, and then VGG ResNets, and then the best results acquired by the hierarchy-aware ResNet. So we can look to these numbers, we can make these objective comparisons, but we can also have a more qualitative look on how these taxonomies look like, especially if we look specifically in some of the subtrees that we have here. So this is a visual analysis that we performed to understand, so why would the HA ResNet be better than, for example, VGG16? What's happening inside those taxonomies that we extracted? And this is the subtree for amphibian, okay, that we extract. And what we can see two things here. First, the red dashed arrows indicate wrong axioms according to the ground truth, and the green arrows means that we got that axiom correct. And we see that we have much more mistakes from the VGG16 taxonomy, and we have some axioms that are very difficult to explain. So for example, our taxonomy for VGG says that a plant is a subclass of amphibian. So, you know, we have some axioms that are very weird in a sense. In the HA ResNets, we still have mistakes. Of course, these models are not capturing the perfect semantics between the classes, but we have a more reasonable taxonomy for this type of models. There are also some other things that we are still exploring, in the sense that some mistakes are intuitively more acceptable than others. So for example, here we have the subtree of primate. This is for hierarchy-aware ResNets, okay? We say that the ape is a subclass of primate, for example, which is correct. But then we say that the monkey is a subclass of ape, and a great ape is a subclass of monkey. So these are incorrect axioms according to the ground truth, but we have this intuition that it's more plausible to say this than to say that the plant is a subclass of amphibian, right? So the idea here is that in going to the future work already here, we're still trying to understand if we can measure these mistakes in a different way to create a better measure for semantic adequacy. Okay, so some final remarks for this work. So we propose this taxonomy extraction method, and we show that the semantic adequacy can enable a semantic comparison between trained CNNs. We can do these comparisons in a very objective and quantitative way. We show that even when CNNs are not trained specifically to recognize such relationships, hierarchical relationships, we can still extract those taxonomic axioms from CNNs. However, when we induce the model during the training phase with some type of knowledge, we can induce some more semantic adequate models, and I think this is an encouraging way to think that we can look for more smart ways to do this knowledge injection part, and because now we may be able to measure it. As future work, one of the things that we want to say is that we are measuring like the taxonomy globally for now, okay? But it might be the case that some models capture parts of the taxonomy better than others. Like maybe one model is going to capture well the amphibian subtree, but it's not going to capture well the dog subtree. And this is what we're trying to measure, like more fine-grained way to measure the semantic adequacy, which is what I call here to provide a local semantic adequacy in order to do that. And also this idea that some mistakes might be less wrong than others, because if you look at the ground truth, the path similarity between different entities might be super large, like plant and amphibians should have a high path between them. In ape and monkey, for example, they are wrong, but they are still close to each other in the ground truth. We need to take that in consideration as well, and also consider other type of architectures beyond CNNs and image classification. So for now, anything that we can create a co-activation graph with, we may be able to use this taxonomy extraction method. I hope you like the presentation, and I just want to finalize it by saying that we have some opportunities in Dublin, in the Insight Center for Data Analytics, to work with symbolic artificial intelligence and combining neural and symbolic AI. And you can get in touch with me. I'll be presenting a poster out there, or you can contact directly my supervisor by email. Thank you very much.
Okay, thank you very much for the presentation. Do we have time for questions? We have another extra mic. Yeah. Any questions from the audience?
Hi, thanks for the presentation. I was wondering if you tried to analyze if there was a link between the places in the taxonomy where the models were correctly labeling or incorrectly constructing the taxonomy, and then the errors that the model was doing at classification time on those parts of the taxonomy. Like if he got the taxonomy right, then he's more likely to do good predictions on that part of the taxonomy. Do you have studied those type of links?
Yeah, thanks for the question. It's very interesting. We actually are trying to do this right now. Like this is a way to evaluate the meaning of our taxonomy as well. The problem is that it might be the case where the CNN, the decision making for the CNN for two similar classes, the decision-making process is very similar, but somehow the CNN is not making mistakes between that classes. And then comes a badly annotated example, and then we get a mistake between a dog and, let's say, an airplane, okay, because of noise in ImageNet and so on. So what we are verifying is that sometimes mistakes do not happen between classes in the same cluster, which is what we expected at that first time. But we think that this is not the best way to measure whether we are capturing these taxonomies in the right way because of this phenomenon that happens between mistakes, you know. Hope that answered the question. Yeah.
Any other question? I have otherwise one myself. Because I'm quite interested on when you say that what is an acceptable error. I think, I mean, you could exploit it. You have an ontology behind, no? You could exploit this. You have some sort of disjointness, no? Something that indeed shouldn't be a subsumption, no? It shouldn't be in the taxonomy because there are two different classes. Have you considered exploiting additional knowledge apart from the taxonomy, like the disjointness between axioms or other type of axioms?
You mean different types of relationships that are not only taxonomic axioms?
Yeah, exactly.
So that's actually one of the things that we plan to do in the future as well, especially because some of these works that I showed you, I'm not sure, maybe you're already familiar with these works, but these works that they extract taxonomies from knowledge graphs, they also extract some type of other axioms, you know. So it may be feasible for us to extract not only hierarchical relationships, but other type of relationships between the classes. But we still wanted to have this first intuition. So let's see if the model has at least captured some type of hierarchical relationships between them, and then we can move forward to see other type of relations between them.
Okay, thank you.
No problem.
Maybe one more question? Yep.
Thank you for the talk. So actually, I was wondering, when you are injecting this knowledge, right, whether you have already any thoughts about the characteristics of this knowledge structure that you inject, and what is their impact on the whole process? Does it make sense? Is it important that it's an ontology with a lot of axioms, or should it be a large knowledge graph? Do you think it will have any impact, and what could be these characteristics?
Yeah, yes, no, definitely. If we find smarter ways to do this, I think we can capture not only a better semantic adequacy, but better, even when we make mistakes, we make better mistakes in terms of the taxonomy. So what we did here, so the part of the knowledge injection is actually not part of my contribution here in this work. So that work, what they did was that they proposed this for AlexNet. What we did in our work was we adapted this to ResNets. Okay, and it's a very simple way to inject this type of knowledge. I think you agree, like just trying to predict more things throughout the learning phase. And it already improves because it makes the convolutional filters, I mean, that's the evidence that we got, that it makes the convolutional filters to understand more about not only the final output classes, but also the hierarchy that we injected upon. But yeah, I think that motivated by the results that we get here, we now need to explore how we can do it better.
Okay. Thank you.
No problem.
Let's talk about this.
Okay, thank you. So yeah, if there are no more questions, let's thank the speaker again. Then our next speaker will be Alessandro, that is presented Deep Symbolic Learning, Discovering Symbols and Rules from Perceptions. And the floor is yours.
Okay. Good morning to everybody. I'm Alessandro Daniele, and I'm presenting Deep Symbolic Learning, which... Okay. Deep Symbolic Learning, which is a work made by myself, Tommaso Campari, Sagar Malhotra, and Luciano Serafini. This is about a Neural-Symbolic framework, which has two interesting characteristics. The first one is that the internal latent representation are discrete, even though the method is trainable end-to-end with back propagation. The second one is that we don't provide knowledge. We are capable of learning end-to-end both the perception function, which maps perceptions to symbols, and the underlying knowledge. So in some way, we are capable of solving some simple instances of the symbol grounding problem. So throughout this presentation, I'm going to use the MNIST addition task as an example. So I think we all know it, but here a slide. So we basically have two images of two MNIST digits, and we want to predict their sum. And the point here is that we don't just want to predict the sum, but we want that the model inside predicts the right digits. And so the difficulties about this problem comes from the fact that we have a very weak supervision. So we know that the sum, for example, here is 8, but there are many consistent predictions that provides that answer. And the general architecture that most of the works we use, and also in our case we use it, consists of a perception network followed by a logical reasoner which performs the sum. In our case, we don't know that it's a sum, we want to learn it, and we don't really have a logical reasoner, but we assume that there is a symbolic function that we want to learn. So basically, the problem now becomes a little bit more complex because at this time, the consistent predictions are basically all the possible predictions because we don't know what is G. And in this work, actually, G is represented as a lookup table. So we just check the corresponding element inside the table to come out with the actual answer. So, as I said before, the idea is to discretize the prediction of the network and also have a function that is discrete. And this allows actually to have a method that is quite scalable. So how do we discretize the predictions? The idea is to use the reinforcement learning approach. So basically use policy functions. So in reinforcement learning, we have a set of possible discrete actions that the agent has to select. And the policy function here selects the discrete action. And in this case, we consider the greedy policy and the epsilon greedy. In the presentation, I will only talk about the greedy policy, but everything I will say about it, it's also true for the epsilon greedy. So in our case, so in the case of reinforcement learning, we have a neural network that predicts an expected reward for each action, and then the greedy policy just selects the action that has the highest expected reward. And then we have the agent received the actual reward, and this reward is used as supervision for the expected reward. In our case, rather than having actions, we have symbols, and we don't have an expected reward, but we interpret the prediction of the neural network as truth values in fuzzy logic. And more in details, we are going to use the Gödel semantics, where the conjunction is represented with the mean operator. So let's look at the architecture. In this slide, we assume the knowledge to be given. Later on, I will explain how we learn also that part. So we have the two input digits, and also the target true value with the y. And like every other methods, we just run a neural network that has as activation function a softmax, and this returns basically a distribution of the possible digits. And when we apply the policy function, we just select the digit, the symbol with higher truth value. So in this case, the higher truth value is 0.4, which corresponds to symbol 1. And that's the prediction of the network for this specific digit. Of course, we do the same also with the other digits. And here we have the internal outputs that are two discrete symbols, S1 and S0. And both symbols have an associated truth value, which are 0.4 and 0.6. So as I said, here we assume knowledge to be given. So we have the prediction 0 and 1, and the final output is then a 1. And it is important to notice that this prediction is correct if both the internal predictions are correct as well. So, and what is the truth value of both the prediction be correct at the same time? If we use fuzzy Gödel logic, it's just the minimum between the two. So basically, this is the DSL architecture, and basically we have a single output for the sum, which is 1, and a corresponding truth value, which is 0.4, which actually can, in reality, it's a lower bound on the truth value of S1. And as I said, we are using reinforcement learning. So what we basically do is check if the prediction is correct. And in this case, you can see it's not. And so we generate a label which is 0, that says that this is wrong. And the idea is basically that this becomes the supervision for the truth value of the predicted symbol. So basically, we are saying the truth value of the conjunction of the two symbols must be 0 if the output is wrong. And notice here that the mu is just a max, and then we have a min, so we have min and max and min, and both functions have all 0 partial derivatives except for the argmin and the argmax. So for example, here, if we calculate the partial derivative of the loss with respect to T2 star, we actually have a 0, because that's not the minimum value. On the other hand, it will be 1, it will be a positive value for T1 star. So basically what happens here is that when we calculate the gradient follows a single path along the architecture until it reaches the softmax, and then it spreads out inside the neural network architecture. And this is nice I think, for two reasons. The first one is that we can interpret the gradients in a symbolic fashion. So we can, for example, look doing debugging during training, check the gradients, and understand what is doing inside during training. And also, what is interesting is that basically this allows the model to traverse the combinatorial space, discrete combinatorial space during training. So what happens here? What it happens is that now we are going to update the neural network's weights, and this is going to reduce the truth value associated to symbol 1, since the prediction is wrong. And since the T1 is the result of a softmax, the other symbols will increase. So basically, the hope is that after that, we will select a different symbol the next time. And now we have, in this example, the right prediction this time. So this time, when we check if the prediction is correct, we have a label equal to 1, which means that we want to increase the truth value of the conjunction of the two symbols. So again, when we calculate the gradients and we apply backpropagation, we update only one of the two neural networks. In this case, they are the same, but they can be also different. And in this case, we exploit what we learn, what we found out to be correct. So this explains how, in this example, we assume the knowledge to be given. Before explaining how we learn the knowledge, I will introduce another variant of the task, where instead of having two images in input, we have only one, and the sum is between the digit represented by the image and a constant value, a constant digit. So still an integer between 0 and 9, but it's always the same for all the possible examples. So the question is, how do we change this architecture? And the solution is quite simple. Rather than discretizing the output of a neural network, we directly discretize some learnable parameters. And the method works exactly the same, but this time, instead of learning the parameters of the neural network, we learn the parameters associated to the constant that we want to learn. And so, in a nutshell, what I wanted to show with that example is that with the policies, we can, if applied on continuous learnable parameters, we can use them to simulate discrete learnable parameters. And the paper is mostly about this. So we saw that if we take a vector of truth values and apply the policy, we can select a single discrete value. If we do the same with a matrix and we apply the softmax and the policy only along one axis, then we can obtain a vector of symbols. And similarly, if we have a tensor and again, we look only in a specific axis, we can basically create a matrix of symbols, which is our lookup table that I was talking about before. So in this example, the W is a 10 by 10 by 19 matrix. And yes, if let's say that the digits predicted by the neural network are like before, an 8 and a 0. So we select the column inside W, which corresponds to that specific set of indices. And this column is a 19 column, where each element corresponds to a possible output. Or in other words, it corresponds to a specific possible rule. So for example, the first element we have that represents the truth value associated to the rule that says G of S0 and S8 is equal to S0. So if G is the sum, some way here we are saying this rule says that 0 plus 8 is equal to 0, which is actually false in this case. And again, similarly, we have all the possible combination, all the possible rules that can exist are represented for that specific pair of inputs is codified inside this vector. And again, we apply the softmax function on this vector, and we apply the policy function that selects only one value. And so we have these two matrices. This G matrix, basically the lookup table, basically contains all the possible predictions like before. Represents the function that we want to learn, and we can integrate this in the architecture just by using that lookup table instead of the previous one. So the previous one was given. Now we want to learn it, and to learn it, we basically take the corresponding truth value that we calculated with the mu, with the max. And this is added to the min operator. So what does this mean? It means that basically, when the neural network gives an output, internally it predicts the first digit, the second digits, then it provides a specific rule for that pair of digits, and for each of these three choices, it has a truth value that are combined together using fuzzy logic. And so if, for example, the specific rule has a weight which is lower than the weights, the truth values of the two digits, then the gradient will go in that direction and it will change the rule. If instead we have a digit that has a truth value smaller than the others, in that case the rule remains the same and it's the digit that is going to be changed. Okay, so this concludes our information, our introduction on the architecture. So the first experiment was on the mixed addition. We can see that we have very similar results as state-of-the-art methods, and also that is pretty scalable. So we need a lot of epochs, 50, much more than the other methods, but one epoch is very fast because even though we are using reinforcement learning, here we don't need to have a simulation. We can just use mini batches like in supervised learning. So every epoch is very fast and we can run multiple samples at the same times, and that makes DSL quite scalable. You can notice that there is also another line which is called DSL NB. NB stands for no biases, in the sense that we try to reduce the biases that we give to the model about the knowledge, about the underlying function that we want to learn. And so rather than having one neural network for the perception function, we have two of them. And also, we don't provide the exact number of digits. We say, OK, we give just an upper bound. We select so the neural network, rather than returning 10 values, it returns 20 values. And the method is capable on its own to select only 10 of them and just ignore the others. So here we have the results, the final confusion matrix and the learn rules. And you can see that it's not the classical diagonal matrix. And the reason is that we are not providing any supervision on the internal digits, and we don't even have the rules. So basically, the model has to come out with a name for all the possible symbols. But you can see that each column has only a specific element which is very high. And so basically, there's a one-to-one mapping between the symbols that the model learned and the digits. And so to evaluate the ability of DSL to learn the rules, what we did was to find a permutation of the columns of the confusion matrix that makes the confusion matrix a diagonal matrix. And then we apply the same permutation to the rows and columns of the learned rules, so of the G. And you can see that all the values are correct. So basically, it learns all the rules about the summation. There's clearly there is a strong limitation of the method, which is we are using a single matrix. And this doesn't allow us to generalize to longer sequences, for example. So we can learn the sum of 2 digits, but we cannot apply the sum of 2 numbers with, for example, 2 digits or 3. So we generate, the idea is to create a variant of the architecture which is recursive and which has 2 different matrices for 2 different sub-functions. So basically, at each time step k, we have 2 input images, which are x1 and x2. And like before, we apply the neural network and the policy. And we have then a lookup table that calculates the current output, the output at time k. And then we have a second table that takes, again, the previous carry, let's say, and the predictions of the 2 digits, basically, and calculates the next carry. So this is pretty nice. There's just a problem, very small. It doesn't really work. And the problem comes from the fact that it's very complex. And when you have a 2-digit, when you have a number that has multiple digits, if you look up at a specific output in a specific position, and there is a mistake, the mistake could come from different points. So it could be that the current prediction of the images are wrong, that the rules for the carry are wrong, then the previous numbers were wrong, and so on and so forth. So it's very hard to solve. So what we try to do to solve this issue is to use curriculum learning. So we use that architecture, this recursive architecture, but in the first step, we provide only 1-digit long numbers. And in a second step, we gave it 2-digit long numbers. And with this strategy, the method actually works, and it's capable of learning the underlying function. And so here we have the results on the multi-digit sum. And what is cool about this method is that it's very scalable. It scales linearly with the number of digits. Which is much faster than current methods, which basically exploit probabilistic programming usually, or a Neurasp actually answer set programming. And you can see that the other methods at the first time they can reach 2 or at most 4 digits long numbers, and then they go time out. While in our case, we can extend even to 1,000 numbers, 1,000 digits, and it still works. Of course, the accuracy becomes 0 because we are calculating the accuracy on the output number. So if we have 1,000 long number, it's almost not impossible, but it's very unlikely to find all the digits correctly. And so we calculate also a fine-grained accuracy, which basically calculates the accuracy of the correct digits. And in this case, we can see that there's a small degradation of the results of the performances, but which is still quite high even with the very large numbers. So I'm very close to the conclusion. So the pros and cons of DSL. The pros are that we can learn the composition of discrete and continuous function in an end-to-end fashion, and that it's capable of learning, and that we provide only the supervision on the composition of this function. It is pretty scalable, and it's nice also that we can interpret not only what the model does inside, but also what it does while learning. Not at the level of the perception function, of course, but at the level of the symbolic function we can. The cons is that it's still limited in convergence speed, when we have when we increase the number of symbols. So we can at most use 2 or 3 symbols before before it starts to become very slow. And but the curriculum learning strategies, it actually helps to solve this issue. So what are the future work? The first things we want to do is to do better experimental studies to understand the internal behavior of the model, exploiting the fact that we can check the gradients. And the idea is that we want to find sources of inefficiencies and come out with some heuristic that makes the method more scalable. And the second thing is that we want to go beyond just lookup tables and come out with something more expressive, let's say. And actually, these are not really future work, are present work, in the sense that we already started to work on these 2 aspects. And I will give just a little spoiler. We were able, indeed, to improve the scalability, and now we are capable of learning multi-digit scenario without curriculum learning, up to 3 digits long numbers. And also we are starting to change the framework to have a Turing-complete language. And the idea would be we don't just want to learn always everything. If we know if we know something, we want to inject that. And so, yeah, that's conclude my presentation. And thanks for the attention.
Thank you. Any question? Oh, okay, very good.
Thanks for your presentation. Can you go back to the architecture slide? The architecture slide, I have a question about that. So I was really fascinated by the fact that you can scale up to 1,000 digits, and I was wondering how the weight matrix would scale with the number of digits. That's something that I didn't understand. Yeah, I can.
Okay. The point here is that we have not one matrix, but we have 2 matrices. Actually, a lot of matrices are tensor, 3-dimensional tensor, because we have 1 dimension that corresponds to the first digit. So it's basically very similar to how we learn summation. We use some each column and calculate the carry.
I see, okay. That makes more sense. Thanks.
Thank you very much for your very interesting presentation. I really like your approach. I think it's really, really similar to also something that we are working on and we have a poster later if you want to check it out. But what I wanted to ask you is, do you think that this method could scale to scenarios where you don't know which, let me call it concept, which terms has to enter into the rule for the prediction that you have to make to solve the final task?
That's a really good question. So basically, if I understood well the question, the point here is that we are providing some biases, which are the compositional structure of the entire task, right? And I think it can be done. I have some idea about it, but still there's it's a future work that I'm still thinking about it. But basically, the idea would be to have the symbol that you predict. The idea is to use the symbol as an index of a vector containing functions and use it to build, and repeating this to try to build a composition. But I don't know how much it could scale, and it's still an open question.
Thank you very much.
Hi, thank you for your presentation. I'm wondering how does this method scales with the complexity and the size and the number of concepts in the rules? Especially, okay.
So here I can show all the experiments. For example, we did experiments where we tried to have a mathematician
Thank you for your presentation. Just a bit more of a clarification on the question just prior. So is at the heart of the system, is it trained on all possible combinations of single digits? Have you tried training it on just a part of the combination and then seeing how it does on the others?
Okay, if you use, of course, it would not work because it's like
Yeah.
we are basically training each element on its own.
Yeah.
It could be, we could, in this case, we were interested in experiments with the idea of giving no biases and see if, without telling anything, it can learn. And of course, if you don't if you know nothing about the function, it's very hard to predict, to generalize to a scene combination of inputs. But think about, for example, we can inject some knowledge. So, for example, you could say, look, I know it's a summation, but I know that it's a symmetric function. So rather than having an entire matrix, you can just say, okay, we select an order and select the preliminary position on the. And in the case, you can so if you so 3 and 2, you generalize to 2 and 3. In general, the more biases you introduce, the easier it becomes to do something.
Okay.
So unless there is a very pressing question, let's thank the speaker again. Okay, thank you very much. So our next speaker is Fernando Zapa Camacho, and he's presenting from axioms over graphs to vectors and back again. And I need to download them. The floor is yours.
Okay. Yes. Okay. Thank you. Okay. Good morning, everyone. So this work is an evaluation. It's related to graph-based ontology embedding. So it's an evaluation of the current methods that exist for this purpose. So to begin, ontologies, they encode a large amount of background knowledge. More specifically, in the biomedical domain, we have large theories like the gene ontology with more than 50,000 classes, and also there are other ones like the human phenotype ontology. So leveraging the knowledge in these ontologies is important because it can enhance machine learning models that perform some predictive tasks like protein-protein interaction predictions or protein function prediction. So as an example, we have a protein-protein interaction. So we have a protein interaction network, many proteins that we know that they interact. So we would like to discover new potential interactions, right? So we could do some kind of link prediction over there. But we have also the gene ontology, which is a taxonomy of functions for proteins. So it's not only a taxonomy, there are more complex relations there. But we have also information about the proteins and the functions that they have. So we can integrate the interactions and also the functional annotations into the gene ontology, so we can leverage this knowledge. And it can enhance the protein-protein interaction task. So in the gene ontology, we have description logic axioms, and we can also put the interaction information as axioms and also the functional annotations as axioms. So we are extending the ontology that we initially have. In that case, the protein-protein interaction problem will become an axiom prediction problem. We want to predict new axioms in our ontology. So there are many ways in which the information in ontologies can be leveraged or can be used in a machine learning model. So one way is using graphs. So this is a two-step process because first we have to transform the ontology axioms into a graph, and then we have to take the graph structure into a real valued space like Rn. So the first step, we call it a graph projection, and the second step is a graph embedding. So after we get to the Rn, we would like to do the step back so we can generate predictions. So to go to the Rn to the graph, we will do some link prediction. But then we also have to use the graph to generate new axioms. So in the second part, from graph to Rn, there is a lot of study. There are many methods, and they have been widely analyzed. But in the first part, to move from ontology to graphs, there are methods, but they have not been properly analyzed. So that's what we have done here. We have focused on this step and characterize this a bit more formally, and also describe some properties that we think are important for the predictive task. So before, first some definitions. So we have ontologies. They are structures. They can be defined using a signature. Basically, we have 4 sets. C are concepts in the ontology, R are roles or maybe relations, and I are individuals. We also have a set X of axioms that can be constructed using these concepts, roles, and individuals. So the elements in C, the concepts, can be also constructed using syntax. This syntax here, we can do intersection of concepts, union of concepts. We can do some existential and universal restrictions, and so on. And using the concept descriptions, there is also something called the general concept inclusion, which are axioms like of the type C subclass of D, where C and D are arbitrary complex concept descriptions. We also have graphs. They are also structured. They have a set V of vertices, a set L of edge labels, if they are relational graphs, and also a set E of triples, which are 2 nodes connected with some edge label. And then we defined a graph projection function, right, as a function that will map the structure in the ontology into the structure of the graph. So this function will map the concept names into nodes in the graph. The roles, depending on the method, it can be edge labels, or it can also be nodes in the graph. But every projection function will map every axiom into a set of edges in the graph. So once we characterize the transformation from ontology to graph as a function, we can define some mathematical properties for it. So the properties that we have chosen are totality, invertibility, and the use of domain knowledge. I will explain each of these in a moment. And the graph projection methods that we have chosen that exist there, it's all2x star, onto graph, and the RDF rendering of all axioms. So first, the methods. We have all2x star. So originally, all2x star is not only a graph projection method. It includes more data, and like textual annotations and so on. But we just took the graph projection part. So this method defines a set of fixed projection rules. So for example, if we have an axiom, as you can see there, it will generate 2 edges, one from C to D and from C to E, labeled with relation R. But if we, for example, change in that axiom the intersection by a union, we will get the same set of edges. And also, if we change the existential for the universal, we will get again the same set of edges. And also, there are some operators and some axiom patterns for which there are no rules, so not all the axioms will be considered. Secondly, we have also onto graph. This is a different method from all2x star because it does not define a fixed set of rules, but you have to define a set of patterns to query over. For example, in the example that we have there, OnToTo graph can generate edges from C to Xi, where each Xi will be all the classes that are equivalent to this intersection between D and E. So to generate these Xi concepts, this method uses reasoning. So it will query all the classes that are equivalent, or maybe subclass, depends on the pattern that you define. And in the end, we have the RDF syntax tree. So this is a syntax tree basically of the axiom. So every axiom can have its own syntax tree. However, trying to use this as a graph will introduce a large amount of blank nodes. For example, in that case, you can see there are like 5 blank nodes that are not reused. So every axiom will have its own blank node. So the graph becomes very, very large and more sparse. So once we have, now we have several prediction methods. So first we defined, we analyzed these methods under some properties. So the first one was totality. So a total function, by definition, is a function that is defined for all the domain. So in our case, the domain is the set of axioms. So here, a function will be partial, for example, if it only considers some of the axioms, for example, the green region, and it ignores other axioms in order to create the graph. And it will be total if it just takes all the axioms, right? So we chose this property because we think it's important to have total functions, because if you generate the graph and then you embed this graph and want to make a prediction of, want to make some prediction of some axiom, maybe this axiom relies on part of the missing information, so the prediction will not be accurate, because the crucial information for this prediction will be missed. So that's why we think it's important to have total functions in this case. We also have the invertibility property. So we define invertibility in terms of injectivity. So in this case, if 2 axioms map to the same set of edges, the method will not be injective. And if 2 axioms map to 2 different axioms map to different set of edges, the projection method will be injective. So we also think this is important because, for example, if you want to query one axiom to compute its plausibility score, and the method is not injective, the score that you get in the graph part will be the score for all the axioms that map into that graph. So you will not have unique scores per each axiom. And the third property that we analyze is the use of domain knowledge. So you have your ontology, the green part, and by reasoning you can generate more axioms, right? So all the axioms that you can entail from the initial ontology will be the deductive closure of the ontology. And there are some methods that can explore this region in order to generate the graph. So now that we have the properties, we can say how each method each method behaves under these properties. So for example, in AL to X star, this method is not total because there are some operators like negation. There are not rules for negation, or for some very complex axioms, there are not rules for it. So it will miss some information in ontology. And also it's not injective because, as I said before, we have this axiom that generates these 2 edges, but if we change to a union instead of intersection, it will still have the same set of edges. So many types of axioms will have the same set of edges. In the case of OnToTo graph, it depends because here you have to define the set of patterns. So you can make the projection total if you define patterns for maybe every type of axiom, but it will not be feasible because it uses reasoning. So doing all these queries will not be feasible in practice. So in the end, you just take a fixed amount of patterns to query over, and then the function will become just partial. And in the same way, depending on the patterns that you choose, this can be injective or not. And the RDF syntax tree, this is totally injective because it uses the syntax tree, so every axiom has its own syntax tree, and different axioms will have different syntax tree, at least in the edge label. So it's total and injective. So to evaluate the properties of these different methods, we set up an action prediction task. So we define action prediction as we have a function f, right? Takes an axiom and it will return some value from 0 to 1, which will represent the plausibility of this axiom to hold true in the either in the ontology or in the deductive closure of the ontology. So I have talked about the first part, the ontology to graph part. So for the second part, the graph from Rn, we have chosen just standard methods that are existing, which is a trans-C method. It just scored triples of the graph based on translation. So translating the head by the relation should be approximately similar to the tail. So it's in the learning process, you try to minimize the score of a positive triple and you try to maximize the score of a negative triple. We also use a trans-R, which is follows the same idea as trans-C, but it just assumes that the nodes behave differently if they are with different relations. So they have learnable matrices that are relation specific. So we use two data sets. We use the gene ontology for it. It has more than 50,000 classes and 9 roles. And we also use the food ontology. It has more than 30,000 classes and has more roles, has like 30 roles. And the way in which we did the action prediction task is the following. We first, well, we did two cases. We did a deductive inference case in which training in the axioms in ontology, we try to predict axioms in the deductive closure of the ontology. So it's similar to what an automated reasoner would do. And in the second case, we did more like an ontology completion task. So we remove some axioms in the original ontology, and therefore the deductive closure will also be smaller because it has less axioms. So in this case, we try to predict the axioms that are missing, the axioms that are missing in the deductive closure. So we evaluated two types of axioms, C subclass D, where in C and D are both just name concepts. And we computed ranking metrics, like we ranked this axiom that is supposed to be positive over all the other potential axioms by corrupting the D, taking all the possible name classes. And also we tested another axiom, a bit more complex. It includes an existential quantifier. So in this evaluation, we predicted the C subclass D axioms and C subclass X are the axioms, right? So the first thing that we noticed is that we expected that the RDF method, which is totally injective, can perform better than the other methods. However, we noticed that the large amount of virtual nodes that it has hinders the predictive performance of it. So it actually doesn't have better performance than the other methods. So when we analyze onto2graph and all2vec, we noticed that, well, we analyzed and we saw that they explore different regions of the ontology. So they have some overlapped information, but they also have some information that onto2graph cannot look at and all2vec cannot look at with respect to each other. So in general, we saw that all2vec star is good in metrics like the hit at k, but it suffers from outlier predictions. So there are some predictions that are true, but all2vec will rank like they are not, but it will rank like they are false actually. So that increases the mean rank. So it's not very good in mean rank metric. However, the onto2graph method, due to the reasoning step that it does, it's better, like in general, to rank the axioms very high, but it's not as good as all2vec in the hits at k matrix. Right? So it's because how these two different methods, the information that they use in the ontology. and also to evaluate the injectivity property of the methods. Because as I mentioned before, in All2X star, if we have these two axioms, they will generate the same triple, right? So computing the score of the triple will give automatically the score of two axioms, but this is not actually true in the real life. These two axioms may have different plausibility score. One, maybe both are true, or maybe only one is true, the other is false, right? So to compute the effect of this property for every method, we set up this evaluation procedure. So we tested all the axioms C subclass exists RD, right? By ranking over all the axioms. The battery. Okay, yes. So first we evaluated all the axioms C subclass exists RD by ranking over all the other axioms by replacing the D concept for all the potential Ds, right? And in the second case, we also included all the axioms changing the quantifier. So in this case, we can evaluate two non-injective methods like All2X star and Onto2Graph, and one injective method. So here we can see that from case A to case B, well, Onto2Graph and All2Back, they perform better than the RDF, right? RDF actually doesn't do very good in the case A, but when we move to case B, the mean rank for Onto2Graph and All2Back will trivially just double, because now they have two axioms. Per each existential axiom, there will be the universal axiom that is scored with the same number. So the mean rank just doubles. Whereas in the RDF case, since it now can recognize the different axioms, it will potentially rank the different axioms with different scores. So we can see that methods that are injective, like RDF in this case, can be better in a more general axiom prediction setting. So just to sum up, so the purpose of this work was to analyze the current graph projection methods, because this analysis, as far as we know, it was not done. So we think that understanding these methods under these properties can also be useful for future developments, so trying to overcome these limitations. We have our code available. It's for free use. And also, if you have some questions, please ask, or maybe reach us in the poster session. Thank you.
Any questions? I have a couple of them. I might be biased, no? I mean, I'm not biased for All2Back, but I may. So you mentioned that All2Back doesn't do reasoning, or I misunderstood? Because we do take into account the reasoning output, but I don't know, maybe I misunderstood.
No, you can do like reasoning before applying like the projection method, right? But the point was that with respect to Onto2Graph, like Onto2Graph is like reasoning based. Like to generate an edge, you have to do the reasoning if you want to generate an edge. In All2Back, you don't necessarily have to do this. You can just generate the graph, or you can maybe previously do some reasoning, so you augment the ontology and then compute the projection.
Yeah, although there are some rules to propagate the information that is in the ontology. It's not like, in some cases, full reasoning, but it does like this propagation. And in the end, we created like some rules to do the projection for us, which was quite handy. Yeah. Okay, and another question I have. I mean, the results are not, I don't know if there is more question from the audience, otherwise I continue. Yeah, the results are not completely surprising, especially for All2Back in itself. No, it wasn't meant really to go back to axioms. Actually, it was meant to be used in combination with Word2Back in the end, no? Because the main contribution was creating some sort of projection of the ontology so that it was keeping correlation among classes, but the lexical information was also key. And that's why we oversimplified ontology, because we only were caring about things that they appear together. So we wanted them to appear together also in the document, and then so that Word2Vec was creating something. So indeed, then you try to reverse back to the ontology, then the results. I mean, I'm surprised that it's still not doing too bad, no? In comparison with onto to graph, and then that's true that the deserialization to RDF is in principle complete, but it's very noisy. So I'm not surprised that Word2Vec sometimes get lost, and then trans-C or trans-R probably will be really affected. And then the question I have is, have you tried other models? Because also my fear is like maybe, apart from the fact that maybe All2Vec is already simplifying a lot, trans-C, trans-R are not maybe the greatest to do this prediction of triples or axioms. So it might be good to try some other models as well.
We just stayed in the translational setting. I think we also tried trans-D, but results were not very nice. So we just took trans-E and trans-R to show like how these properties affect. But I agree. Maybe All2Vec was not designed to do these tags, but there are some cases where we use All2Vec because we can just have a graph representation and then combined with graph-based machine learning, which there is a lot of it out there. So we can just leverage it. And
it's a good analysis in any case, to get some additional insights. Yep.
Yes, thank you.
So, do you have more questions from the audience? No. Someone is coming from the semantic web, maybe. No. Otherwise, let's thank the speaker again. Thank you very much.
Thank you.
Okay, as the saying goes, all good things come in three. So, third round of my preferred NeSy2023 game, poster pitches. Alessandro Oltramari unfortunately couldn't make it due to bad weather conditions at the US East Coast when he tried to leave. On the other hand, Danny Silver is spontaneously pitching in because he wanted to assure that you did not forget about his spotlight presentation yesterday. So if you missed it, you'll get the short version again after all the other poster presenters. Good. Ideally, I would now have a speaker at that mic over there. And your time starts now.
Hi everyone, I'm Mihaela, and later today I will present our paper titled Exploiting T-norms for Deep Learning in Autonomous Driving. In our work, we wanted to show that we can define memory-efficient T-norm-based losses, given that standard implementations fail to scale to complex scenarios. Our task was event detection, and we used for this the dataset RODAR. As we can see on the right in the plot, the standard implementation in purple only covers about a quarter of the constraints in RODAR. On the other hand, our memory-efficient T-norm-based loss can significantly reduce the memory costs, and it makes it possible to use t-norm-based losses for events, for tasks such as event detection in autonomous driving. So if you want to know more details, please come see our poster. Thank you.
And your time starts now.
So, hello everybody. My name is Mulo Defrangen, and I'm excited to introduce you our new challenging dataset for evaluating knowledge graph embeddings. Next. In the field of knowledge representation and reasoning, when we deal with knowledge graph and representation, there is many intriguing tasks to solve, like link prediction. And one effective approach to do that is using knowledge graph embedding models. Next. Typically, when we evaluate knowledge graph embedding, we extract dataset from knowledge bases. In our case, we focus on three bases. Next. There are some well-known datasets used many benchmarks. Next, like Freebase 15K and Freebase 15K237, and many others. And the main goal in designing this dataset was making the task more realistic and non-trivial inference. Next. So, in fact, you can see here that that in literature they've been widely discussed. Next. And also been evaluated many against knowledge graph embedding models from state of the art. Next. As the example, here is an example that shows the nomination of some songwriters to a special award. Next. However, this presentation, we found some flaws in it, such as compressing the relationship and making them more atomic and not representing any relation. And this led to some information loss. Next, so to address this issue, we propose to create an exact subset of Freebase. Next, by introducing nodes called CVT, which is common value type, and intermediate node that will help us to represent any relation and more complex relation. Next.
10 seconds.
We have conducted some fair evaluation on this dataset, and it revealed that some baseline from knowledge graph embedding model are having hard time to have good result to this challenging dataset. Next. And if you're curious enough to join, to know more about the evaluation on our dataset, please join us at my poster. Woo!
And go.
All right. Hi, everybody. So this is our work on explainable classification of internet memes. Next. Internet memes are complex. They are multimodal. They are relatable. They depend a lot on what we know in our context, on our cultural community knowledge. They are fluid, and they are succinct. This makes it very difficult to detect hate speech in memes, which is actually pretty present out there. The additional challenge to this is that if we use black box methods, which is against the state of the art, this is not really useful for human experts. So regardless of whether the prediction is correct or incorrect, it makes it pretty difficult to know what to do with it. So the opportunity that we saw here is to exploit case-based reasoning to create explainable methods for meme classification. Next. So this is our methods in a nutshell. We have a two-step method starting from feature extraction and then going through using two different kinds of case-based reasoning. We are using multimodal feature extractors that are aware also of slang in some of these, in the memes. And then on the right side, I showed the two different case-based reasoning methods. So one is example-based reasoning. The other one is prototype-based reasoning. Next. And so our results in a nutshell show that if we use case-based reasoning, we are able to retain the accuracy of the classification, but also get some initial way to explain what the model is actually doing. And we have additional nuances in terms of
I like it when people bring their own clock.
right? And we show some additional nuances in terms of the impact of the different modalities. I will also talk about our user interface that we developed to showcase this explainability. Thank you.
Okay, hi.
Go.
So next slide, please. Okay, concept-based models are models that support high-dimensional inputs and do not give up on interpretability. So how do they work? Next. So they map the input to concepts, to a vocabulary of concepts in a black box manner. And next. And from these concepts, they combine them in a white box manner to give a prediction. So next. So as long as the concepts are interpretable, the prediction admits an explanation in terms of the concepts. Next. But how can we ensure the concepts are interpretable? Next. So there are many heuristics in practice, but there is no clear definition of what is the interpretability of these concepts. Next. So there are many approaches that directly supervise what are the concepts. Next. But next. It has been shown that still it is not enough. So there is this phenomenon called concept leakage there can be spurious correlation among concepts that destroy their semantics. So next. What we do is to give a notion of interpretability based on causal disentanglement. We explain what is concept leakage in terms of lack of auto-distribution generalization, and we propose glance nets, a model that avoids leakage and gives you interpretability. Thank you.
Do we have a presenter for that one? Okay, let's go with closed world assumption. Yep. Go.
Okay, hi everyone. I'm Lucille from the UC Louvain, and the motivation behind the work I'm presenting today is that in a lot of domain application, we are in need of classifiers that are not only accurate but also interpretable. And usually the method to learn such classifiers are either symbolic or using neural methods. But if I'm presenting here today is because we tried to combine both works. And so the thing we wanted to learn was a fully interpretable neural network that could learn ordered rule list and could perform binary, multi-class, and potentially multi-label classification. And this using a very standard neural network training and not like specific application of it. So on the next slide, you can see the kind of network we obtain at the end. And I will not describe it now, but I just want to stress the fact that the rule description that you see on the right is an exact translation of the network. And so if you feed an input to this rule description or the network, we would have exactly the same prediction at all time. So on the next slide, the potential application for this kind of network is, for example, the potential of applying different loss function to learn this rule, or also the possibility to learn the rules and the features extractor into one unique differentiable structure. And if you're interested in our work, do not hesitate to come to the poster station. Thank you.
My first word will be next.
Go.
Have you ever felt the need for an interpretable classifier that makes predictions using logic rules and achieves state-of-the-art accuracy without using background knowledge? So basically, in other words, do you need a deep problem where you don't know how to write the logic program, or you don't have the ability, it's unfeasible to build the whole set of logic rules that you may need to solve the problem? Next. If you're interested in this question, answering this question, then this poster could be interesting for you. We have a solution where the neural network generates the logic rules, and then we execute the rules symbolically. So please come to our poster and see what we have.
And go.
Wow. So we had 2 amazing days, right? Looking at all these systems, combining symbolic and sub-symbolic components, looking at the individual systems. It was amazing, but at this point, don't you wish you had more of a bird's eye view, overview of this area, not to talk about individual systems, but about groups of systems which are more frequent, less frequent, and so on. We had such a feeling 3 years ago, more or less, in the semantic web community when the winds of neurosymbolic integration reached our community and more people integrated machine learning and semantic web components to the degree that we were really losing sight of all these systems. So what we did in response was to perform a systematic mapping study, which was accepted at the ACM Computing Systems Journal, and 3 of the authors are also on site, so we are presenting it together. Next. So in summary, we have been looking at a subset of neurosymbolic systems, those from the semantic web community. I will explain this at the poster next. And we found around 500 papers describing such systems only in the last decade. Next. So what to do with 500 papers? How do you put them on a graph like this? So our solution was to take a step back, represent the internal architectures with some system patterns that you see here. What does this mean for you? Can your system be represented with one of these patterns? And what does it mean for the community? Can we use this to have an overview of the neurosymbolic system field? 2 seconds too late, sorry.
Thank you.
So come to the poster to discuss it.
You're working hard these days.
Yeah.
Okay.
All right, thanks a lot. So yeah, hello, I'm Michael, and this work I'm presenting today somehow relates also to the talk I presented yesterday. Namely, we want to address the binding problem or the superposition catastrophe in neural network by representing multiple objects as the superposition of bound symbols in a high-dimensional space. So I showed yesterday how we can kind of map sensory data to this high-dimensional representation, and in this poster we want to do actually the inverse. So how can we disentangle the superposition of bound symbols to get the individual symbols? And the problem is that this actually boils down to a combinatorial problem, as we need to search through all the possible bound symbols. And what we do here in this work is we use a so-called resonator network that can iteratively search through multiple solutions at the same time by doing computation in superposition. So if you're interested why some things like stochasticity, nonlinearity, and sampling can be helpful in this case, drop by the poster. Thanks.
And the final poster pitch of NeSy2023. And go.
Next slide there. Thank you. So based on some rather compelling background information from neuroscience and cognitive science, as well as some just a bit of a review of deep learning, particularly LLMs, we propose a hypothesis. Next slide there. Right, that is presenting the fact that we feel that symbols will continue to play a really critical role, but it's because of their ability to really communicate what we're thinking, as opposed to being the basis of what we're thinking. Next slide. And so if you come to the poster, we can walk through and talk about some of the theoretical aspects of how this dual system works to actually help us not only think at a very deep matter in terms of concepts, but to be able to communicate those in terms of symbols, both to each other as well as internally within ourselves. And we can thinking more and more this has to do with reasoning. And next slide, Dirk. And a couple of results I didn't present yesterday, at least on a lot of detail. We can talk about our learning of, again, noisy digits, the full arithmetic suite of operators of division, multiplication, subtraction, addition. And last slide, also something very similar, and that is in object detection and how learning the features can help explain not only how well the accuracies of your predictions, but more importantly, where it makes mistakes, where the errors are made, so it can explain how it makes errors. Thank you.
Perfect. Okay, thank you everyone. Coffee break is yours.